Welcome back to BE 110 Continuum Mechanics. Last time we introduced the stress tensor by considering the components of the tractions acting on the faces of a unit cube aligned with our unit vectors. We further imagined that each of these tractions, these normal and shearing tractions acting on each face, were equal and opposite on opposing faces, and so therefore the cube was automatically in equilibrium with all the forces and moments balancing. But in general, the stresses in a continuum would be continuously varying. So we need to come up with a derivation for the equilibrium condition on the stresses in a real non-homogeneous continuum. So to do that, we're going to start by considering this elemental parallel pipette with infinitesimal dimensions dx1, dx2, and dx3. Now you can see on the back faces here are the tractions we defined before. So this is the one face, and normal to that is sigma 1, 1, the normal stress in the x1 direction. And then there are two shearing tractions, sigma 1, 3 and sigma 1, 2. Similarly, on this face, we see sigma 2, 2, sigma 2, 1, and sigma 2, 3. And on this lower face, we see sigma 3, 3, sigma 1, 3, and sigma 2, 3. These are defined just as we did before, although these are actually the negative faces of this parallel pipette. But we're assuming that these stresses are changing, so that using a Taylor series expansion, we would see that the stresses on the opposite side would be incremented by a little bit. So for example, sigma 1, 1 on this face would actually be sigma 1, 1 plus del sigma 1, 1 del x1 dx1, etc. So let's just start by demonstrating that. So consider the stress sigma ij to be changing continuously. And hence, from Taylor's theorem, and truncating after the first derivative term, the stress at x plus dx1 for the sigma 1, 1 component will be sigma 1, 1 at x1 plus dx1 and x2 and x3. Would equal sigma 1, 1 at x1, x2, and x3 plus del sigma 1, 1 del x1 times dx1. And we can write a similar expression for all the other components and faces. And so you see them here on this diagram. By the way, I'm using sigma here just because I got this picture from a book that happens to use sigma as the notation. I prefer capital T, but I'll use sigma to be consistent with the diagram. So now we can do a force balance of these components. And we'll start with the x1 direction. So this direction here. We'll balance all of the forces, the shear forces and the normal forces that are going in the positive or negative x1 direction. So we'd start with this term here, sigma 1, 1 plus del sigma 1, 1 del x1 dx1, minus this one here, it's on the negative face, sigma 1, 1, times the area of that surface, dx2, dx3. Plus the shear tractions that are pointing in the x1 direction, in this case on the x2 face, so sigma 2, 1 plus del sigma 2, 1 dx2 times dx2 minus sigma 2, 1 times dx3 dx1. And then finally, the shearing tractions on the 3 face. So sigma 3, 1 plus del sigma 3, 1 dx3 times dx3 minus sigma 3, 1 minus this term here. And then plus a component of the body force in that direction, which we would multiply by the volume, since this is body force per unit mass times mass per unit volume would give us body force per unit volume times volume would be force. Now, if we divide this entire expression through by dx1, dx2, dx3, which is just the volume of that elemental parallel pipette, you can see that these terms here cancel with these ones there, and we're left with del sigma 1, 1 dx1, we're dividing these out, plus del sigma 2, 1 del x2, plus del sigma 3, 1 del x3, plus rho times b1. And we can similarly do the same thing in the other two directions and get analogous expressions. Del sigma 1, 2 del x1, plus del sigma 2, 2 del x2, plus del sigma 3, 2 del x3, plus rho times b2 equals 0. So that's the x2 force balance. And finally, in the x3 direction, we'll get del sigma 1, 3 del x1, plus del sigma 2, 3 del x1, plus del sigma 3, 3 del x1, plus the x3 component of the body force. So these are the 3 force balance equations for a material continuum in equilibrium. It's the balance of the surface and the body forces. They're equal to 0 because there's no inertial forces. There are 3 equations because the forces are a vector, but they're derived from the stresses, or at least the surface force contributions come from the stresses. And if we just look at these equations, you'll see that in each case, we're getting the component of traction in the 1 or 2 or 3 direction. Remember, it's the second index of the stress that refers to the component. The first index is the face. So then we're summing up the contributions of those tractions from the first face, the second face, and the third face. So this is the force balance for x1, force balance for x2, the force balance for x3. And therefore, in general, we can write these equilibrium equations for a continuum more compactly using index notation as del sigma ij del xi. And notice again, it's the first index that we're taking derivatives with respect to and summing. So the I is repeated. And the free index is j, so this is 1, 2, 3, plus rho bj is equal to 0. So this is 3 equations for j equals 1, 2, and 3. Or in direct notation, and I'll switch from sigma to t here, we would write that as the divergence of t plus rho times b equals 0, or div t plus rho b equals 0. Now, I don't want to confuse you with this notation here. I would ordinarily have used Tij rather than sigma ij, and since I've used the convention of a capital letter for a tensor, I didn't want to introduce a capital sigma here. So there's nothing special about this. I'm just essentially changing notations from sigma to t. Now, equilibrium also requires that the moments balance. So in the same way, we can take moments about 3 axes and derive 3 moment balance equations. If, for example, we start by taking moments about the x3 axis, then we can ignore any forces that act through that origin and calculate the contribution of the remaining tractions to moments about x3. So that would include contributions from sigma 1, 1 here and sigma 1, 1 there, with a moment arm of dx2 divided by 2. So therefore, we get sigma 1, 1 plus del sigma 1, 1 dx1 times dx1, so this force here, times this area, dx2, dx3, times this moment arm, dx2 divided by 2. Plus, for this positive moments in a right-handed sense about x3, sigma 1, 1 times this area, dx2, dx3, times the moment arm, this moment arm here, which is dx2 upon 2. Next, we'll get contributions from the shear stresses acting on this face, which will be sigma 1, 2 plus del sigma 1, 2 dx1 times dx1 times the area of the face, dx2, dx3, times this moment arm, which is dx1, minus sigma 2, 1 plus del sigma 2, 1 del x2, dx2, this traction here, times this surface area, dx1, dx3, times the moment arm, dx2, plus sigma 2, 2 contribution of this and this. So this traction here is sigma 2, 2 plus del sigma 2, 2 del x2 times dx2 times this area, dx1, dx3, times the moment arm, this distance here, which is dx1 over 2, minus the moment due to sigma 2, 2 here, which is sigma 2, 2 times dx1, dx3, which is the area, times the moment arm, dx1 divided over 2. And so on with the other components. This one here, sigma 3, 2 plus del sigma 3, 2 dx3 and times dx3 and sigma 2, 3. And this one here, sigma 1, 3, and this one here, sigma 3, 1 plus del sigma 3, 1 del x3 times dx3. And those ones again have moment arms of dx1 divided by 2 and dx2 divided by 2. And then finally, components of the body force in the x1 and x3 directions, sorry, the x1 and x2 directions, acting at the middle of the cube, will also contribute. So there's the big ugly expression we get for the moment balance. Now we'll divide through by dx1, dx2, dx3, and take the limit as dx1 tends to 0, dx2 tends to 0, and dx3 tends to 0. And what that does is get rid of just about everything except sigma 1, 2 and sigma 2, 1. So it leaves us with sigma 1, 2 minus sigma 2, 1 equals 0. Or sigma 1, 2 equals sigma 2, 1. And similarly, if we take moments about the x2 and x1 axes, these will lead to sigma 1, 3 equals sigma 3, 1, and sigma 2, 3 equals sigma 3, 2, or in general, sigma ij equals sigma ji. In other words, the stress tensor is symmetric for a material continuum in equilibrium. We'll later show that this is true even when the body isn't in equilibrium.